Okay, thank you for having me. So the PAPYRUS project, it will bring a newly developed pathfinder for pyramid wavefront sensing techniques on Sky. And this initiative is led by PhDs and postdocs all over France, with support from senior staff members and ONERA, Alpau, LAM, OHP, and funding from LAM in our Wolf, LabX Focus, and ASHRA. So the pathfinding instrument, it will be installed at the Coudet focus of the 1.52 meter telescope at Observatoire de Haute-Provence. We'll present the design in a few slides, but this same telescope is famous for the early demonstration of astronomical AO with the COMAN instrument. So it's very interesting that we're planning to go back with a pyramid to this telescope. So how good is the seeing at OHP? If my slide updates. So the seeing, the typical seeing is between 2 and 4 arc seconds in the visible. So an R naught of 3 to 5 centimeters is to be expected. And as you can see, it rarely drops below 3 centimeters, the R naught. And most of the year, it's actually not cloudy. So the goals of our Pathfinder are threefold. First of all, we want to use it as a tool for teaching and outreach, to use the system for master's classes and summer schools, such as the one given last week at OHP, and to help young researchers gain experience in instrument development and AO systems. Then secondly, we want to use it as a research and development testbed for taking pyramid wavefront sensing control algorithms from the lab on Sky. And thirdly, our goal is to provide access to AO-corrected imaging at OHP. So for the expected performance, we did some simulations based on the available hardware that we already had in store, which was focused on a 17 by 17 DM. We ran some tests on using a workstation as an RTC, and we can reach about 300 Hertz with 2.5 frames latency. Now, in a noiseless scenario, I mean, in a photon noiseless scenario, this would give us a trail ratio of around 10%, given reasonable seeing conditions at OHP, which means that we go from 2 to 3 arc second seeing to close to the diffraction limit. And regarding the flux, we know how many photons we need in our pupils, and we have calculated that we can get this amount of flux at 300 Hertz around magnitude 3 or 4 stars. Here is a layout of our optical design as designed by Eduard Muslimov. It uses mainly off-the-shelf components in combination with existing hardware that's available at LAM and at our collaborators. In this design, the telescope Coudet focus comes in from the left here, and the focus is found here around this red dot. And from here, we pick it up and place our off-the-shelf components and our different different optics. So first of all, we have a DM in the shape of a 17 by 17 Alpau DM on loan from ONERA. Our baseline for the RTC is a regular workstation that we know works up to 300 Hertz. And we are collaborating with Alpau on a dedicated RTC that would potentially allow increased performance. Secondly, our wavefront sensor is based on an existing glass pyramid and an OCAM 2K detector. And our science camera is a Hamamatsu Orca. And both the wavefront sensor and the science camera will share the light at a central wavelength of roughly 700 nanometers. Now, this bench will be installed at the Coudet room underneath the telescope. So there's a platform for visiting instruments here. The beam comes in like this, and we'll pick it up here. So first we'll do AIT at LAM, and then move to OHP to install this as a visiting instrument. Now, to be able to use this instrument while in the lab and in adverse weather conditions, we have designed a telescope simulator that will be placed in the beam, and this would allow us to generate turbulence using an SLM and a laser source as a light source. So this will allow us to align the system and to do some testing in case we can't go on sky. Now, our outlook, initially in our timeline, we would have been on sky already, but unfortunately we were unable to go to the lab and to OHP for several months. So at the moment we're finalizing the design, ordering the components, and which means that in November we should be able to start assembling this instrument. And by the end of the year, we should have an integrated instrument in our lab that will be running initial testing. So hopefully early next year, we will go on sky and at OHP, and we can show you some exciting new techniques. So thank you for your attention and for the support of all our collaborators listed here. Thanks.
Okay, thank you, Gilles. I'm going to. So there is no question in the Slack. Has anyone a question? I do have one. While people think, is how do you separate the light? So you're saying you are sharing the light with the science camera and the wavefront sensor. So what share of light are you sending to each of them?
At the moment, it's a 50-50 beam splitter at this location, or beam splitting plate. And so sending half of the light off to the wavefront sensor branch and half of the light to the science branch. Potentially, we could also put a dichroic here, but then we would have to replace the science camera for something that is more optimized for instance, Y or J band.
Okay, and my next question is related to what applications are you planning to do with these at your OHP?
So yeah, so the science, it is quite, rather limited, because if we want enough photons, we only have, and if we go close to zenith, we might only have about 20 stars at any given time in the year. But it would allow us to do some close to diffraction limited imaging on these stars. But our main focus is definitely the using it as an R&D testbed.
So there is a question by Carlos. Can you go ahead, please?
Just one button to unmute. Sorry. So I saw your simulation, Gilles, and I was just wondering, since you're indivisible, right, and with a pyramid and a relatively large sink, at least with respect to what we're used to deal with, if you took into account optical gain or optimization in this.
So these simulations were done with Olivier Beltrame-Martin and Jeff Sauvage. So I can't really comment on the exact parameters that were used during the simulation. Maybe Vincent Chambouleron knows a bit more about what went into these simulations. But
I can maybe I can answer this question. So no, we didn't optimize. I mean, for this simulation, the optical gains. I mean, we played with the loop gain to have good performances. But yes, it could be more precise with the optical gains. And actually, I mean, so Gilles didn't show. I mean, kind of a new part of this bench where we will put some solution to solve the optical gains. I mean, of course, the R&D tests we want to do on this bench are mainly focused on the optical gains of the pyramid. Of course, you may have understood that. So we will try the optical gains on this bench a lot.
And so what would it mean if I get, sorry, jump in, if I understand this correctly, is that you'll be monitoring the PSF on the tip of the pyramid and then draw the optical gain information from that?
Yes, exactly.
And the last question is one by Gilles de Chivry. Could you please go ahead and ask, Gilles?
Yes, hi. My camera, yeah. I was just wondering that, if you expect any effect from scintillation, since you are sampling quite a lot the atmosphere, and that you have relatively strong seeing. So I was wondering if you look into that, or if you expect any effect from that.
Vincent, do you have an answer?
No, so we really didn't look into that, into scintillation for this.
But that's a good point, and definitely we would like we're gonna look into that. I don't expect to have too much trouble, but yeah, it was to be analyzed. Yeah.
Yeah, just in terms of robustness,
yeah.
maybe in the wavefront sensing measurement that you might have, dropping flux locally or something like that.
No, it's a good point. It was to be analyzed.
Okay, thank you. We have to proceed to stay in time.